Hi, in this video, I want to continue my series on causal analysis using R with a more sophisticated example of Bayesian networks. Okay. So in this video, we will present an example of using the R package bnlearn for Bayesian network analysis. And we cover the following topics. First, generate a mixed type synthetic data set, and then applies multiple structured learning algorithms and fits parameters, then perform arc strength estimation and model averaging, and visualize networks using Bayes and advanced plotting, and demonstrate classifiers, and then handles missing data, and then do a little bit model comparison. Okay. So first, let's generate our data set, load the library mass for multivariate statistics, set a random seed, sample size 500. This is the variance covariance matrix. So we generate the multivariate normal distribution for continuous data, give them names. We have 3 continuous variables. And then we create 3 discrete variables as a binomial, actually Bernoulli distribution. And then we load the library MNet to generate a multinomial distribution. So, and this is the data set. You can, there's 7 variables, 3 continuous, 3 discrete, and 1 multinomial. So the mean R package for Bayesian network analysis bnlearn, we load that, and we want to also use the library Rgraphviz, and this is a very complicated library. So the R codes I posted here are kind of an easy way to download and install it to your RStudio. So I load that, and now I'm gonna do structured learning using HC, which is a hill climbing algorithm, and also GS is a growth shrink algorithm, and the taboo search algorithm, and also the max mean or maximum minimum hill climbing algorithm. Okay, so after you fit this structured learning using different algorithms, then you can fit parameters using the bn.fit function. So it's pretty simple, so you can get the bn fit. And also you can visualize the network structure. So this is the basic plotting. So you divide the canvas into 2 by 2. You plot out these 4 different network structures. Okay. So you can see that different algorithms lead to different structures. Each structure has its strengths and weaknesses. And so you may ask which one we choose, right? So you need to do some model comparison and model selection, which is a pretty complicated topic. We'll touch upon it toward the end of this video, okay? So here is just a demonstration that you can do different structural learning here, okay? All right, so the next one is using the more sophisticated graphing tool, the Rgraphviz.plot. So this is nicer organized. You can see the edge, so continuous 1, continuous 2, continuous 3, discrete 1, discrete 3, and discrete 2 and multinomial are by themselves. Okay. And graph.plot is more sophisticated. It can generate better looking graphs for publication. So that's the difference between this sophisticated graphing function versus the Bayes plot function. Okay. All right, the next one is we want to do conditional queries and prediction. So Bayesian network, we can use it for prediction once we fit the model. So we can use the CP query. So print CP query bn_fit event equal to discrete equal to 1, evidence continuous 1 greater than 5. So what does this do? So this is computing the conditional probability of discrete 1 equal to 1 given continuous 1 greater than 5. Okay, so which is that's like 0.367. And we can also do for continuous variables, for care continuous 1, we can form a data frame that as the data, which is discrete equal to factors of 1, levels equal to levels, Bayesian data at discrete 1. So these options just to prevent error messages, so that it looks across all the levels for discrete 1. Okay, so what you can do is you can perform it to give you 4.984. So since your target is continuous variable, it's going to predict the conditional mean given discrete 1 equal to 1. Okay, so, and if a continuous 1 is a categorical variable, then it's going to predict the category closely. It's a predicted value close to that category. Okay, so if you feed the data equal as a new data frame, you have new data, new observation, you form a data frame, then it will predict for the new data. Okay. All right, next topic is arc length via bootstrap and the model averaging. So arc length is a pretty important concept. So we can do boot.strength function. We're doing it on the HC algorithm. And then we can do model averaging. We can average all the networks. So we have R equal to 200, then we have 200 bootstrap networks. So we average them out, and we can plot it out. It look like that. Okay. So this shows some stability of the HC network structure. Also, we can calculate the arc length using the arc.strength using the arc.strength function, and you can print it out. So the arc length is the measure of confidence or strength of each arc, or what we call directed edge. Right? The strength, a numerical value, is the difference of network scores, such as BYC. More negative strength means stronger edge, stronger arc. Okay. So, for example, in this example, you can see the table here get a couple of numerical values here. So you get continuous 1 to continuous 2, negative 64.76, continuous 2 to continuous 3, negative 35.46. Discrete 1 to discrete 3 is negative 4.22. So you can see the strengths of the first two edge are much stronger. Okay, so the more negative, the stronger the edge is. Okay, so discrete 1 to discrete 3 is somewhat interesting, but it's a little bit weaker. Okay, so this is kind of how we interpret the arc length. All right, I want to borrow the package E1071 to do the naive Bayes, to do machine learning, a naive Bayes model. If we do the naive Bayes model, we use the multinomial, regress and other variables, and use the naive Bayes function, and we can print it out. It has the predictions for the multinomial variable, okay, categorical 1, 2, 3. Okay, and then we can do predictions for existing data or new data. You can feed the data equal to Bayesian underscore data, or if some new data, it will do the prediction using the Bayesian model. Okay, yeah, naive Bayes model. Okay, and then you can actually predict the prediction table or the confusion matrix. So you want to see a large numbers on the diagonals, and then small number on the off diagonals. So here it's mostly pretty accurate, especially if predicting like a B and a B, those. But it doesn't do well for the A and the C, right? So, but anyway, so this is give you an idea about the accuracy of the prediction. Okay. We can also calculate prediction probabilities to give you. So this is the first few rows of the predicted probability matrix for all the observations. Okay. And you can pick the category with the largest probability to do the classification. Okay. All right. Next topic is more complicated. How to handling missing data using EM algorithm. So assuming this missing data is missing at random, right? So first you can create a Bayesian data missing. You can just randomly assign, the missing values. And then what you can do is you can create an empty graph for this missing data set, and then you can do a start fit to get it kick-started. Then you use the structural.em, so this use the EM algorithm to do imputation. Okay, so it's going to take in the Bayesian data missing data set, start with start fit, maximum iteration 10, maximized by HC, and scoring is BIC CG, and then it put everything in the result underscore all. So first, the key components of this object is first you can visualize the natural structure, which is similar to the first one, right? So it's pretty stable. And then you can look at the imputed values. So this is the data set imputed, so it's a complete data set. And you can also look at the fitted values. Okay, so this is give you some of the fitted probabilities here. Okay, the last topic is really just comparisons. So here we have two model structures. We can do the compare function and it give us this output. So what this is it's going to use the first one as the gold standard. So this is saying, okay, these two, like true positives, like a BNHC doesn't really catch any edges in the bn.gs. Okay? And the false positive is it's not in bn.gs. There's 3 in the bnHC, and false negative is there are 4 in HC but not in GS. Okay, and since we don't know the true structure of the network, so this is not comparing to a gold standard. So this is just saying these two network structure we learn are very, very different. Okay, so but if you insist that I want to know really which one is better, we want to calculate the BIC value, then you can do it. First, you need to extend the GS, BNGS, because it's not a complete DAG. So you must extend it first, and then you can use the score function to calculate it. The BICHC, it is a complete one, so you don't really need to do the extension. You can calculate it, and then you can print them out. Yeah, they are actually very, very close. They're very close to 2871.302. The other one's 2871.207. Okay, so very, very close. But it looks like the BNHC has a little bit smaller BIC value. So using this approach, you can calculate different BIC values, and you can compare models. And of course, model selection is very complicated. You have to consider domain knowledge and maybe many other criteria just to think about it. Okay. All right. It's almost toward the end of the video time limit, so I'm going to stop here. Thanks for watching. Have a good day.